Every major glass manufacturer from Germany to Japan has spent the last decade chasing the same holy grail, a window that cools a building without blocking the view and generates power without needing a separate solar panel. China just got there first. Researchers in Shanghai have now demonstrated a window film that drops surface temperatures by as much as 23 degrees Fahrenheit while feeding a measurable electrical current back into the building. 23 degrees, you heard that right. That is the difference between a summer afternoon and a spring morning on the same pane of glass. And the temperature drop is not even the part that has competitors worried. The part that has them worried is what this film does to the economics of an entire industry. Hit a quick like and subscribe now, because by the end of this video, you will understand exactly why glass manufacturers everywhere are suddenly paying attention. But first, let's talk about the glass currently sitting in nearly every building on Earth. Ordinary window glass earned its place in modern architecture through more than a century of engineers proving it could do exactly what buildings needed. Engineers love it because it is transparent, structurally simple, and endlessly reproducible on assembly lines from Shenzhen to Stuttgart. Manufacturers love it because a single float glass process, invented decades ago, can churn out sheet after sheet for just a few dollars per square foot. Governments love it because building codes already trust it completely, and no regulator anywhere questions whether a pane of glass belongs in a skyscraper. That trust was earned, pane by pane, across 100 years of skyscrapers, greenhouses, and storefronts that never once failed the people standing behind them. Here is the part most people never stop to consider. A single large office tower can carry more than 100,000 square feet of glass, an area roughly equal to 2 soccer fields stacked vertically. Every one of those square feet lets in light for free, cutting the daytime lighting bill in ways cheap plastic or metal paneling never could. Glass also survives wind loads and decades of rain without degrading, which is exactly why architects never seriously entertained replacing it. So why did nobody solve the one obvious problem sitting in plain sight for a century? The problem is not that glass fails. The problem is that glass has only ever been asked to do one job. It lets light in. It does nothing with the heat that light carries, and nothing with the energy hiding inside that sunlight. A material this trusted and this proven should have been the perfect platform for something more. Instead, it has simply sat there, transparent and passive, for generation after generation of buildings. Think of ordinary window glass the way you might think of a kitchen colander. A colander has exactly one job: let the water through, keep the pasta back. Nobody asks a colander to also dry the dishes or heat the stove. For 100 years, glass has been architecture's colander, and nothing more was ever expected of it. Here is the part that puts the scale of this in perspective. Commercial buildings consume more than 30% of their total energy on heating, cooling, and lighting combined, roughly the same share of a household budget most families spend on rent. Every pane installed since the 1960s has been optimized for clarity and strength, never for energy generation, because nobody thought a colander needed to also be a power plant. That silence is about to end. Glass held its job for 100 years, and it never once asked for more. The vulnerability hiding inside ordinary glass is not a manufacturing defect. It is a design limitation baked in from the very first pane ever floated on a bed of molten tin. Glass was built to be transparent, and transparency and energy generation have always been treated as opposite goals. The same way a window and a solar panel have always been separate products, bought from separate suppliers, installed by separate crews. This is not about window glass being a bad product. It is about window glass being an incomplete one. Quantify what that incompleteness actually costs. Air conditioning alone accounts for roughly 70% of peak summer electricity demand in major Chinese cities, a load equivalent to running every washing machine in a city the size of Chengdu simultaneously, non-stop for the entire afternoon. Meanwhile, the glass on every one of those buildings sits there converting 0% of the sunlight hitting it into anything except heat that then has to be pumped back out at enormous cost. Two failures, stacked on top of each other, on the very same surface. Here is the part that most building owners never think about. Every dollar spent cooling a glass-heavy building is a dollar spent undoing what the glass just did. Sunlight comes in, heats the interior, and then air conditioning spends energy fighting the very light the window let through in the first place. It is a closed loop of waste, repeated in office towers and apartment blocks across every hot climate on Earth, and it has been treated as simply the cost of having windows. The consequence shows up hardest in exactly the places least equipped to absorb it. Hot, dense, rapidly urbanizing cities across Southeast Asia and the Middle East pay some of the highest per square foot cooling costs on the planet, precisely because glass towers are the fastest and cheapest way to build upward. The flaw is not evenly distributed. It falls heaviest on the cities that can least afford it. For decades, researchers proposed reflective coatings, tinted films, and low emissivity layers, and each one traded away light, view, or cost to buy back a little efficiency. None of them solved the underlying problem. None of them made the glass do anything more than sit there slightly less wastefully. Then, in 2023, a research team in Shanghai began answering that question with data that was harder to dismiss than anything the field had seen before. The team behind this breakthrough works out of Shanghai Jiaotong University, in collaboration with materials engineers at the Chinese Academy of Sciences. And their approach did not start with solar cells at all. It started with a much older question about how sunlight itself is structured. The core idea sounds almost too simple once you hear it. Sunlight is not one single thing. It is a mixture of different wavelengths, some of which carry visible light your eyes can see, and others which carry infrared heat your skin can feel, but your eyes cannot detect at all. Previous attempts to build power-generating windows tried to convert the entire spectrum at once, using semi-transparent solar cells layered directly over the glass. That approach failed for a straightforward reason. Any layer thick enough to generate meaningful electricity was also thick enough to darken the window and block the very light people buy windows for in the first place. The new film takes a different approach entirely. Picture a prism sitting flat instead of standing up, quietly sorting light as it passes through, rather than bending it into a rainbow. That is essentially what this film does, using a nanostructured coating just a few hundred nanometers thick to physically separate incoming sunlight into two channels. Visible light passes straight through to keep the window clear, while infrared wavelengths get redirected sideways toward a thin strip of photovoltaic material embedded at the window's edge. Here is the part that changes everything about the economics of the design. Because the film only has to manage the infrared portion of sunlight, it never needs to be thick enough to darken the glass. The window keeps 90% of its normal visible transparency, roughly what you would expect walking past any ordinary storefront, while the redirected infrared energy still generates a measurable, usable electrical current. Earlier coatings failed because they tried to do one job with one layer, forcing a trade-off between clarity and power that nobody could escape. This film succeeds because it splits the job into two, sending each wavelength exactly where it is most useful, without asking one material to handle both tasks at once. Visible light stays where people need it. Infrared heat goes where the electricity gets made. Nothing is blocked, nothing is wasted. That single design decision is the difference between a coating and a power source. But splitting light in a laboratory is one thing. The real question was whether that split would hold up outside it. Here is the honest number first. The infrared harvesting film currently converts only about 8% of the redirected infrared energy into usable electricity, a figure far below the 20% plus efficiency of a dedicated rooftop solar panel sitting in open sun. On paper, that sounds like a disappointing result for a technology being called a breakthrough, and it is worth sitting with that disappointment for a moment before explaining why it matters far less than it first appears. But here is what that number actually means in practice. A rooftop panel exists to do one job: generate maximum electricity and nothing else. This film is not competing with rooftop panels. It is running quietly on surface area that was previously generating zero electricity at all, on windows that already exist, on buildings that were never going to install rooftop solar in the first place. 8% of something is still infinitely more than 100% of nothing. Anchor that number against how buildings actually use glass. A typical 40-story office tower has a fraction of the rooftop area needed for meaningful solar capacity, but it has a facade several times larger than that same rooftop, covered almost entirely in windows, already doing nothing but transmitting heat. Redirecting even 8% of the infrared hitting that facade generates enough electricity to power the building's interior corridor, lighting around the clock, without a single additional panel ever being installed. Now, for the unexpected advantage nobody predicted going in. Because the film blocks infrared before it ever reaches the interior, it also reduces cooling demand by up to 40% in field tests, a bigger and more immediate financial win than the electricity generation itself. The two effects compound. Less heat entering means less air conditioning running, and the electricity generated helps power what air conditioning remains. There is also a use case already working today that has nothing to do with skyscrapers at all. Vertical farms and greenhouse operators in southern China have begun installing the film because reduced heat load protects sensitive crops, while the generated electricity offsets grow light costs, a pairing nobody originally designed the film for. In one pilot facility outside Guangzhou, engineers recorded a 15% drop in monthly electricity bills, savings that came entirely from a material nobody had previously considered a power source. The question was no longer whether the film worked. The question was how fast it could move from laboratory samples to buildings people actually occupy. The first serious real-world test happened in 2024 on a 32-story commercial tower in Shenzhen, retrofitted by China's Southern Glass Holding, with roughly 60,000 square feet of the new film across its east and west-facing facades. Engineers monitoring the building recorded a 23-degree Fahrenheit drop in interior glass surface temperature during peak afternoon sun, alongside a measurable electrical output feeding directly into the building's lighting circuits. The field matched the forecast. That sentence matters more in this industry than almost any other claim a research team can make. Laboratory samples routinely outperform their real-world counterparts once dust, humidity, and years of thermal cycling enter the picture, and building owners have been burned before by coatings that looked perfect on a bench and failed within 18 months on an actual facade. This time, the numbers held, and they held through an entire summer of the kind of heat that usually exposes every weakness a new material is hiding. Part of why they held comes down to a manufacturing detail that made adoption dramatically easier. The film can be laminated onto existing glass using the same equipment already used to apply standard tinting and safety films, meaning building owners do not need to replace windows entirely, only retrofit them, cutting installation costs by roughly 60% compared to full window replacement. Field monitoring data from the Shenzhen installation has since been made publicly available through China's National Building Energy Efficiency Monitoring Platform, allowing independent researchers anywhere in the world to verify the results rather than relying on the manufacturer's own claims. That kind of open access is rare in a market where proprietary coatings are usually guarded like trade secrets. We stopped thinking of this as a coating and started thinking of it as infrastructure. The moment the electricity readings came back consistent for 6 straight months, one senior engineer on the monitoring team said, "If that surprised you, the next part is going to be even harder to believe. Hit subscribe so you're there when we cover it. It started with one tower in Shenzhen, where cooling cost mattered more than the 8% conversion ceiling anyone worried about going in. Then, it spread outward from there to logistics warehouses, greenhouses, and now residential towers in 3 additional provinces. The claim now had receipts, but one successful retrofit is a case study. What happened next was an entire industry deciding it could not afford to look away. More than 140 international patent families now cite the underlying spectrum-splitting technique behind this film, filed across China, South Korea, Germany, and the United States. These are not academic citations. These are legal and financial commitments, the kind companies only make when they believe a technology is going to matter commercially for years to come. 4 companies in particular have moved beyond simply watching. China. Southern Glass Holding announced a $300 million expansion of its Shenzhen production line in early 2025, specifically to scale film manufacturing to commercial volumes. Saint-Gobain, the French glass giant, confirmed a licensing evaluation agreement covering European markets, a rare move for a company that typically develops its own coatings in-house. Corning disclosed an internal research partnership exploring compatibility with its own architectural glass lines, hoping to combine the film with existing product families already installed worldwide. And LONGi, already the world's largest solar manufacturer, began testing the film's infrared harvesting layer as a companion product to its rooftop panel business rather than a competitor to it, a signal that even solar incumbents see this as complementary rather than threatening. Here is the regulatory driver accelerating all of this at once. China's Ministry of Housing and Urban-Rural Development updated its Green Building Code in 2024 to award additional certification credit for facade materials that reduce both cooling load and grid demand simultaneously, a category this film fits precisely and almost none of its competitors do. The economic logic underneath all of this is simple math, not ideology. In any market where retrofitting existing glass costs 60% less than full window replacement while also cutting a building's single largest energy expense, a 40% advantage is not a trend. It is a competitive pressure no serious property developer can afford to ignore. Here is the detail that puts everything into perspective. None of these companies are making a bet on a promising lab result. They are making a bet on 18 months of continuously verified field data, published openly, sitting on a public monitoring platform anyone can check against the manufacturer's own claims. That kind of transparency does not usually accompany a technology this early in its commercial life. Usually, global momentum arrives only after the honest limitations have been weighed against the field data and found still worth the investment. Industry analysts project that if this film were installed across just 10% of China's existing commercial glass facade within the next decade, it could offset electricity demand equivalent to the annual output of 2 mid-sized coal power plants, a scale roughly comparable to powering every home in the city of Hangzhou for a full year. There is a meaningful secondary benefit sitting alongside that projection. Reduced cooling demand at that scale translates to an estimated 18 million metric tons of avoided carbon emissions annually, roughly equivalent to removing 4 million gasoline-powered cars from the road. And because the film retrofits onto existing glass rather than requiring new construction, it offers a path to emissions reduction that does not depend on tearing down a single building. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. The infrared photovoltaic strips embedded at the window's edge currently rely on a rare Earth-adjacent material whose global supply is concentrated in just 3 countries, creating a bottleneck if demand scales faster than mining capacity. Manufacturing precision for the nanostructured layer still requires cleanroom conditions that add roughly 12% to production costs compared to standard tinting film. Long-term durability data currently extends only to 18 months, well short of the 20-year warranty period building owners expect from facade materials. Retrofitting older buildings with non-standard window frames can add installation costs that erase some of the 60% savings seen in newer construction. And building codes outside China, particularly in the United States and the European Union, have not yet created a certification category for dual-function cooling and generating facades, meaning approval timelines in those markets remain genuinely uncertain. Here is the part that keeps this honest rather than promotional. None of these obstacles are hidden or downplayed by the research team itself, and every one of them appears in the same published data that made the breakthrough credible in the first place. None of these challenges change what the science shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as an engineering one. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate demands is a different question entirely. That question does not stay contained to windows for very long. The story of window film that cools buildings and generates power is ultimately the story of what human civilization can build and where it can build it. For most of architectural history, comfort and electricity have been separate purchases, available only to whoever could afford both the building and the systems layered on top of it. That gap falls hardest on exactly the places least equipped to close it. Rapidly urbanizing cities across Southeast Asia, South Asia, and parts of Africa are building glass towers faster than almost anywhere on Earth, precisely because glass construction is cheap and fast, and precisely because those same cities face the harshest cooling costs on the planet. A retrofit film that lowers both the electricity bill and the cooling bill using windows already installed is not a luxury upgrade. It is one of the few climate technologies that gets cheaper exactly where the need is greatest. What is genuinely new here, not incrementally better, but categorically different, is a single surface performing two jobs that have been sold as separate products, on separate budgets, by separate industries, for the entire history of modern architecture. That is not a minor improvement. It is a different category of solution. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the climate demands is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists. That is new. Technologies that touch every window on every building on Earth compound in a way most breakthroughs never get the chance to. A 10% gain in a single factory saves that factory money. The same gain applied to every glass surface on the planet reshapes how entire cities are cooled and powered for decades. If a single film can turn a window into a power source, it raises an obvious question about what happens when the glass itself is redesigned from the ground up, not just coated after the fact. That story is worth understanding too, and it is the subject of our next video. China's new glass generates electricity and cuts energy cost by 75%. The link is in the description. If this changed how you think about the windows in your own home or office, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every 2 weeks. Now I want to hear from you in the comments. Should governments mandate energy-generating window retrofits on existing buildings, or should this stay a market-driven choice left entirely to property owners?